Thanks everybody for coming. Great to see you all, or see your names and see where you're from. Appreciate you all joining. Um, my name's Luke Sonnet. I'm the head of experimentation at GrowthBook. I'm joined today by Ronny Kohavi, former VP and technical fellow at Airbnb and Microsoft, co-author of the excellent Trustworthy Online Controlled Experiments book, and well-known Maven instructor. So he'll share more about his background in a few minutes. Today we're going to be talking about red flags to catch before you ship a test result and making sure your experiments are trustworthy. A bit of housekeeping first. This session is being recorded. We'll send out the email to everybody within a few days. Please, feel free to use the Zoom chat for, quick comments or clarifying questions. But there is the Q&A function that we will be using for questions at the end of the webinar. If you can't see it, it should be at the bottom of your Zoom under More. There's a Q&A button down there. That'll help us both see ones that are upvoted by you all, so you can also go in there and say and vote on some of the questions that you think are most important for us to answer. When the session's going to end, a short survey will pop up, and so let us know what you thought so we can help improve these webinars. Next slide, please. So yeah, our agenda today, Ronnie's going to be talking about the anatomy of an untrustworthy A/B test, walking through a real test that's claiming a huge lift, walk through some red flags that it may be missed and are associated with this test around missing power calculations, sample ratio mismatch, and so on. I'll pick up from there and I'll cover two issues that can be more subtle at times, like peaking and multiple comparisons, and how they can cause you to ship with way more uncertainty than you thought you were shipping with. So we'll wrap with some practical solutions in your questions. Then there's going to be a raffle for attendance in one of Ronnie's courses. We'll be raffling off 3 spots in his course, and we'll have a Q&A, and we love to answer any and all of your questions. So with that, I'll hand it over to you, Ronnie.
Thank you very much. Let me start with a little bit of an introduction about myself, who I am. I got a PhD in machine learning from Stanford. I went to Amazon, director of data mining and personalization, and one of my teams was WebLab, which is the Amazon experimentation system. This is where we got exposed to some interesting ideas and success rates. I then went to Microsoft for almost 15 years, led the analysis and experimentation team. Fairly large scale at the time I was there. We were starting about 100 new treatments every workday. It has now ramped up to about 300 a day. So the scaling still continues beautifully. I then went to Airbnb, relevance, personalization, and experimentation. And then, as you may know, I wrote the HIPAA book with 2 co-authors, and it has been translated into some of these languages that you might find more easy if you're from that country. I'm now consulting and teaching about quarterly with Maven and some private classes. So I want to start with a kind of an interesting anecdote here. When John F. Kennedy in 1962 gave a talk at Rice, he said the following.
We choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard.
And what I see a lot today is many organizations saying, we do this not because it is easy, but because we thought it would be easy. And this is where controlled experiments fall a lot. It looks trivial. You run this t-test and you get the results, but there are lots of gotchas that you want to be aware of. A/B tests are the gold standard in science, but to get the trust, you need a lot of effort. And, one of the articles we wrote in 2010 said, we see that, getting numbers is easy. Everybody's able to publish all these. Getting numbers you can trust is hard. And that's one of the key themes today, showing you that you have to run some sanity checks and look for red flags. So we're going to use this motivating example. It's an article that was published recently, and it made the following claims. 44.8% lift from 55 to 80. The details of the treatment was not important. It was definitely buzzword compliant. We're using all this cool AI. It's got to work. And then it said 99% confidence. which the author wrote, means we can be 99% certain their results reflect a genuine difference between two pages, not a statistical accident. We're going to analyze that, show that this is not true. They wrote that they split visitors equally across two variants and had 54,000 people or users per variant. Again, we're going to see why this is not as accurate as claimed. Of course, their conclusion is AI smashed it right out of the park, and we have lots of questions about whether this is actually correct. Okay, so let's go and analyze and dissect this example. So the first one, and one of the things that's really, really important when you run A/B tests, make sure you understand the concept of power. Power is not mentioned in this article. It appears that no power calculation was done, and the numbers are tiny. I'll show you the numbers as I compute them and estimate them. Very, very important. If you want to read an article, I co-authored this one with a few of the luminaries in the field. We have Andrew Gelman, who has some of the seminal articles on power, who's a co-author. We have Guido Imbens, who's a Nobel Prize winner. So pretty top-notch people saying, hey, this is essential. So what is this power calculation, right? What are we really doing here? It's just a simple formula that allows you to compute the minimum sample size. But it needs some parameters, and this is why it's a little harder and people just don't do it. So some of the parameters are easy, like you need the variance, or in the case of conversion rate, you need the conversion rate. You need to decide on alpha, industry standards, let's say 0.05. You need to decide on power. Again, industry standard is 80%. Then the problematic parameter, it needs the MDE. What is the minimum effect that you want to be able to detect? And a lot of times we don't know what to put in there. Are we going to detect 0.5%, 1%, 4%, 10%? It's hard. So let me give you some numbers. At Bing, where we run tens of thousands of experiments, the average treatment effect was rarely above 0.3%. Okay, at Airbnb search, successful experiments improved conversion by about 0.3%. If you look at Georgi's article on analytics toolkits, he says the median lift was 0.1% based on a little over 1,000 experiments. So a lot of experiments have very low lift, and we want to set that MDE to be such that we can detect these, right? So it has to be a low number, right? It's the minimum that you want to detect. Now, I'll be realistic. Picking 0.3 is going to be tough. Why? Because it's going to say you need very large samples. And many organizations, many of you out there will not have big enough samples. So there's a trade-off here, and you're going to have to settle and say, okay, I can't detect 0.3. Let me try and detect 2. Okay, for example, in our community project called Trustworthy A/B Patterns, where we are replicating some of the well-known patterns out there, we picked 2% as our MDE for most of the experiments, because that's the type of sample sizes that we were able to get out there to volunteer for this project. As a rule of thumb, I recommend that you never pick an MDE over 5%. I think that's unreasonably optimistic. It is extremely rare to see any result over 5%. So, given the reported conversion rate, she reported this conversion rate of 55.7 from some detail page, you can go into a power calculator and say, okay, if I plug in an MD of 5%, the highest that I'm willing to plug in, you need 10,000 users in the 2 variants. Okay, most of these calculators will tell you 1 variant, and then you have to say I'm running 2 or 3, and you multiply it. So we need 10,000 variants. How many users did the actual experiment have? 300. Okay, so it tells you need 10,000, you have 300. You are severely underpowered. Okay, now I'll also state something which I thought was a little misleading. The author stated 54,000 users per variant, but these are users that entered the website. Only a small percentage reached the page where the change was made. And so when you look at the triggered population, that's the users that are exposed to the change, that these are the users that you compute the sample size for. It was 300. Tiny. Now we could also ask the reverse question. Okay, let's assume we have only 300. What power do we have instead of the industry standard of 80%? Okay, and it turns out to be 6.9 for the right tail, the tail that we're looking for improvements, dramatically below 80%. Okay, and there's a link here if you want to see how I did this calculation. You can go to that. There's a question from Warda about deciding on the winner. That's an OEC question, an overall criteria. You get to pick the MDE based on the metrics that you care about, typically the overall evaluation criteria and some guardrails. And so those give you bounds for the minimum experiment, minimum sample size that you need. Good question. Okay, so let's go back and say, okay, let's say you have low power, 10%. Some people say, so what? So I have 10% power. What is bad about this? So first of all, you're unlikely to get a statistically significant result, right? Because if the result is of the MDE size or larger, you only have a 10% probability of detecting it and calling stat sig. And remember that 5%, right, of the results are going to be stat sig when there is no evidence, right? This is our type 1 error. Alpha is typically set to 0.05. So if there's no effect, 5% of the time you'll make a mistake, a false positive, or a type 1 error. So all you did with this, raising the power to 10% is went from 5% to 10%. Very, very low probability that you will get a statistically significant result. Worse, the winner's curse. This is what we see out there all the time, and this is what I believe we see in this example that we'll share. If you get a statistically significant result in a low power situation, below 50%, then your treatment effect estimate must be exaggerated. Okay, you will get a high result. It will never materialize. Okay, and again, I'm giving you some links here. You'll be able to click on them or ask me for the details. And there's a couple of papers here that are really good. This seminal paper by Andrew Gelman and Carlin showed the following graph, which is amazing. If you're around 80%, you can see that there's very little exaggeration. This is close to 1. But as you go with lower power, you end up with massive exaggeration. For example, with 10% power, so there's 0.1 here, you are going to have an expected exaggeration of 4 times. This isn't 4%. This is 4 times the actual number. Okay, so let's look at our example. If I plug in the power, the expected exaggeration, what is called type M error, the magnitude error, is 5 times. Okay, so there was a claim about like this massive lift. The expected exaggeration is 5 times. The minimum exaggeration is at least 4, right? This is the minimum that you will get as an exaggeration. And the probability of a sign error, meaning you thought the treatment was better, but control is better, is a whopping 9.6%. So there's almost a 10% chance that you're directionally wrong. Okay, now I want you to compare that to the claim by the author that they are 99% confident. I mean, there's not just the probability that this is not effective, but there's a 10% probability that the control is better. Okay, and what I see out there is many A/B tests that are being run with alpha of 0.05, and they're going to generate a lot of false positives, and they're going to exaggerate the treatment effect. And those are the ones that you see in headlines. David asks about Bayesian effects, but affected by exaggeration. Less so. There are still issues, and there's an article by Georgi that you can read about some of the concerns around here. But again, with Bayesian, the problem is you don't get the guarantee that of type 1, type 2 error. If your priors are wrong, then the results are going to be wrong. Okay, this is a fun post I did about praying to Twyman. I just want to show you because it sort of exemplifies the problem here. So, I could report that yesterday I had a 100% increase in conversion rate. Why? I flipped a coin 10 times and I got 3 heads. Then I prayed to my God called Twyman and I flipped it another 10 times and I got 6 heads. So I'm going to write an article saying I had a 100% increase in my conversion rate because I prayed to Tony Twyman. Okay, now, if you send me $1,000, I will send you the prayer. And more than that, 10% of the proceeds will be donated to the education for the gullible. So I hope you realize the absurdity here. These are tiny numbers. Even though this is something you could imagine seeing, an increase of 100%, it is an underpowered experiment, and you should not trust it. But this is really what a lot of the published results out there look like. They don't do power calculations to say that they need larger samples, and they don't show you that they tried 20 prayers until they found the correct prayer, right? By chance. So here's a table that's going to help you. If this is an experiment and you have conversion rate about 50%, say this is a typical checkout process, then you need 12,000 users per variant. Sorry, total. You need 12,000 users for the A/B test. If you're going for something like at the cart, which has a conversion of 20% to checkout, you're going to need 51,000 users. If you're at 10%, meaning let's look at people that initiate checkout, you need 100,000. And then typically a good site will have a 5% conversion rate. You need 240,000 users. If you're in a more expensive checkout process that has a 2% conversion, you're going to need 600,000 users. And then if you're gunning for, something, a rare event like a 1%, you're going to need 1.3 million users. Okay, so these are just examples of the sample size that you're going to need. Heed this, listen to this. It's hard to do experiments when you have 10,000 users because you're nowhere in this unless you are going for a metric that has a 50% conversion rate. Okay, so this is problem one, having to do with power. Let's look at misinterpreting p-values. Very, very common misunderstanding. The author says, I have 99% confidence. A lot of the tools out there give you this number, but she interpreted it as we can be 99% certain that the result reflects a genuine difference between the two pages, not a statistical accident. This is wrong. This is misinterpreting p-values. The 99% confidence is typically corresponding to a p-value of 0.01. It's just 1 minus that. But the p-value is a conditional probability. It is conditioned assuming that the null is true. Okay, what you normally want to say is what is the probability that when I got a statistically significant result, it is a false positive, and this is called FPR, the false positive risk. Now, the problem with the false positive risk is that it needs one more parameter. It needs the prior probability. So before you started the experiment, what is the probability that it will be successful? Right? Bigger than the MDE. So given that it needs this parameter, we can ask, what is that prior probability? Can we get some historical data from organizations to tell us what is the probability of success? Okay, and this is what we've done in this table. Right? You can see that at Microsoft, when we started, there was a lot of QA on every idea. We had a success rate of 33%. Avinash Kaushik, a well-known blogger, says it's about 20%. At Bing, where I worked for multiple years, our success rate was about 15%. Here you have 4 different organizations, Booking, Google Ads, Netflix, and Optimizely. They're reporting about a 10% success rate. And then the last line also comes from me. I headed Airbnb search, 8% success rate. Very hard problem, lots of machine learning, very hard to improve statistically significantly. So once you have the success rate, you can get your false positive risk. This is the number that you want to share with the organization. This is the probability that a statistically significant result is a false positive. And so if we go to the median line, right, this is where most organizations are, and half are equal or below this, half are above this line, it's 22%. Okay, so it's very important that you understand that when you run with an alpha of 0.05, you don't have 95% confidence. You have 22% false positive risk score, but only about 78% confidence. Okay, so remember, summary, the median of this table, and if you don't have this number of success rate, I claim you should use about this number, 10%. And then if you're using a standard of 0.05, that means only 78% are going to be true positive, 22% false negatives. If you are using a higher alpha, like, optimize these ships with a 0.10, then more than a third, 36% of your statistically significant results are going to be false positives. Okay. So remember, the success rate is an unknown parameter. You can estimate it. There's a paper here that we wrote on how to estimate it. The simplest estimation is to look at the number of wins, but there are more sophisticated mechanism using conditional probability that you can use. And some of these have been adjusted based on these estimates. So if we sum it all up and we look at the median success rate, and we say, let's apply to this example where the author said, there's a 1% chance that they're wrong. The false positive risk is 87%. Okay, so the result that was reported is likely to be a false positive 87%. Pretty humbling. Okay, third problem, sample ratio mismatch. This is the number one test that I want to make sure that you run. Okay, if you're running an experiment with equal percentages, which is the typical way that we run experiments, you should have approximately the same number of users in each of your variants. Okay, there's a small question in the chat. I'll pick it because it's relevant. We can get the minimum sample size required, but how do we ensure the sample is representative? If you're randomizing correctly, it will be representative to the users that arrive at your site, which is what's interesting. So it doesn't mean it will replicate on another site, but if you randomly assign people to users and control, then you will get representative samples. And that's the core idea in randomized controlled experiments. And let me also remind you guys, I see some questions in the Q&A. This is better. Please send them to the Q&A. Please upvote on others, and we will have time to answer several of those that were voted high. Okay, so going back to SRM, you ran an experiment, you assigned it equal or unequal. You can still do this test for unequal, but we're going to assume equal percentages, which is what she reported. And I want to run with you through an example, not the example that is here, but an example from Microsoft. We had an experiment where we had a fairly nice number of users in control and a fairly nice number of users in the treatment. And the ratio was 50.2, right? Whereas it should be 50. And one of the questions that you need to ask, well, should I be worried? I mean, this looks pretty close to 50, right? So should I be worried that it is 50.2? And the answer is absolutely you should be worried. With large numbers, such a deviation is unlikely. You can compute the p-value. So because it's a 50-50, we know the prior, the p-value of a split being 50.2 or higher is this small p-value. Okay, so this is supposed to happen only 1 in 500,000 experiments. And since you did run 500,000 experiments, it is likely that you have a problem. Okay, there's a link to a spreadsheet where it's very easy to compute this p-value. Go ahead and use it if your tool does not support an SRM check. Now, the thing that is surprising, and the reason I encourage you all to run this, it happens a lot. I worked at Microsoft. We reported that 6% of our experiments have a sample ratio mismatch. And this is not in the beginning where the ratio starts high. This is after years of running experiments. It is still a huge problem. And then this 6% is reporting relative to a threshold of 0.001, not relative to 0.05, where it would be sort of expected to be 5%, right? So huge number. And then we discuss how to diagnose it. Whenever you have an SRM, it is pain to diagnose the problem. There's another data point here. Convert.com added SRM checks, and they found 6.5% of their experiments have SRM. I'm consulting for multiple companies. If they don't have a sample ratio mismatch, we do it, and the numbers are shocking. Like just this week, I worked with a client. They have a 20% sample ratio mismatch to their experiments. So let's go back to our example. She stated there was a 50-50 design, and the number of triggered users, which is what we care about, was 176 and 124. Okay, that looks off from 50-50. If you do the p-value computation, you will see that the p-value is 0.003. So this result, the SRM, is more significant than the result of 0.01 that was reported That's a dark, dark yellow flag, maybe even a red card for the experiment. Now, one of the things that I hear a lot is, okay, so we have a small mismatch, 50.2. But, how bad is that? So I want to just share with you one example from Bing. Okay, there was an experiment, showed amazingly strong results. These are the key metrics that compose of the OEC for Bing. I'm not going to share the details of them, but you can see increase, 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 increase. P-values, some of them are tiny, 7e minus 11, 2e minus 10, right? This has 9 zeros before the 2. Okay, so pretty nice p-values that you should trust in theory. But there was an SRM. Ratio of users was 0.497. It wasn't 0.5. It was a little bit off. We computed the p-value. Look at the small p-value. Therefore, something is wrong with the experiment. We did the diagnostic. What happened? It's a bot. Okay, so we excluded the bot. Now we had a balance, no SRM anymore, but look at the results now. These are the same 5 metrics as here. None of them are statistically significant. Okay, so be aware that when you have an SRM, it is typically the result of some very skewed effect. That could be bot, it could be something wrong with the pipeline, it could be caching. It's very interesting to diagnose SRMs. But once you remove those skewed users, you might be surprised to see that nothing is significant. Okay, so there's a question in the chat. How often should we check for it? Well, certainly at the end of the experiment. We also check in the beginning. This is more complicated. It's due to the desire to abort experiments that have SRMs. And so you can use some more sophisticated mechanisms to lower your alpha with what's called interim group sequential tests to be able to determine that the experiment is not trustworthy after a couple of hours. Right, that happens. Okay, last problem, Twyman's law. Okay, remember I mentioned before I prayed to Lord Twyman. So in the book Exploring Data and Introduction to Data Analysis, the authors wrote that Twyman's law is perhaps the most important single law in the whole of data analysis. And you might think, oh my God, this is the E equals MC squared. What's coming next? Well, it turns out that what comes next is the simple statement. Any figure that looks interesting or different is usually wrong. And I'm a big fan of Twyman's law. So when you have some extreme result, double and triple check it. It is likely to be wrong. And I've applied Twyman's law a lot and we found a lot of bugs. And notice this goes against our intuition, right? When we have a beautiful lift where we want to celebrate. We want to send an email to the whole company saying we just got this massive lift. Hold it. Think about Twyman's law. Double and triple check things before you send it, because it is likely to be wrong. When I see somebody reporting a 44% result, it triggers my skepticism. I've never seen a trustworthy experiment where the OEC is real, not some, vanity metric that improves by 44%. It just never happens unless the product is broken. Yes, I've seen that. There's this massive bug people can't check out. Yes, you will get large lifts. So I want to end with a few other checks that you should be doing. I mentioned these 4 because they are related to this example. And I said, oh my God, it just doesn't have one test. It has 4 red flag tests that are being violated. The number 1 recommendation is run AA tests. Split your users into 2 groups, just like an A/B test, but there is no difference, right? Hence the name. So if your system's operating correctly, only about 5% of the time should a given metric be statistically significant with a p-value less than 0.05. Right? Easy claim to make. Now, if you're a statistician, you can do better than this test by doing a whole series of AA tests and looking at the distribution. And it should be close to uniform. Right? So you can do a test for uniformity. And if it's off from a uniform distribution, then you have a problem with the randomization or with the computation or with the variance or whatever. This finds a large number of bugs in the systems and in the variance, right? There's a whole chapter of in my book about AA tests and the learning, and there's a nice reference by Simon Jackson that I'm giving here. Bot traffic. People don't realize how much of their traffic is bot. We spent a lot of time on bot detection. At Bing, 50% of traffic in the US was bot generated. In Russia and China, 90% of our traffic was bot generated. So it could be big. It's probably smaller for your site because you're not as famous as Bing, but you might still find a lot of bugs, and they're creating a lot of skew. So you need to make an effort to remove them. Watch out for novelty and primacy effects, right? If your treatment effect is decreasing or increasing with time, it could be due to this. A lot of people are concerned that they have this all the time. It is not common, but it does happen, and you need to watch for it. A lot of the trends that you see initially are just noise, but still, this is something worth doing. So, if you want to learn more about A/B testing, I teach 2 online courses on Maven. We're going to raffle 3 tickets to the introductory class and the Q&A. The first class is Accelerating Innovation with A/B Testing, rated 4.8. It's 5 sessions of 2.5 hours, and there's a discount here of $250 for the first 5 people to register. The second class is the advanced class. There's a lot of selection bias here. Only people that want to really do A/B testing come here. It's rated higher. And again, there's a discount here if you use this URL. And I see that Lindsay put those in the chat, so you have them accessible. I am right on time. I was supposed to end at 9:33, believe it or not. So I am right now perfectly on schedule, and I will hand it over to Luke.
Thanks, Ronnie. Appreciate it. Just give me a second to switch over here. Great. Thanks everyone. Just as a reminder, in Zoom, if you go to the Q&A at the bottom, we'll be taking a bunch of these questions afterwards, and you can upvote some of the existing questions. There's already some really good ones in there. So again, at the bottom of the kind of Zoom webinar screen, you'll be able to see that button that lets you open that Q&A up. If it's not there visible, you can click more and go into that Q&A, and please go ahead and drop your questions in there, and we'll be happy to answer them afterwards. Great. Thanks. Thanks, Ronnie. Hi, everyone. My name's Luke. I'm the head of experimentation at GrowthBook, the leading open source experimentation platform. I'm leading the team building out our experimentation tooling, everything related to statistics, queries, metrics, analysis, all that good stuff. And I have a background working on platform teams at some larger tech organizations. Great. So I'm going to get into a couple other issues to talk about in trustworthiness in experiments. The framing I like to think about is that trusts in experiments are built on the kind of transparency and reliability of those experiments. So a trustworthy experiment gives you reliable information. Statistical significance is a very common signal that people use to rely on to say, we're pretty sure that this experiment is showing us some result. And it turns out, in many ways, explicitly and implicitly, you control that threshold. So one of the standard kind of values you see out there is this alpha of 0.05. This is saying that under the assumption that there isn't an impact, 5% of experiments are going to falsely appear significant. But of course, the kind of question can be why this number? Should every experiment use 0.05? One, there's many inputs into what you want to pick here, or what you should be using. But one of the key concepts I like to think about is whether or not a feature is kind of costly. If it's more costly, then the risk of a false positive is more damaging. Because if it requires ongoing support, if it's going to dictate your product roadmap for the next 3 years, you want to be really certain that you're shipping things that are going to not just drag your organization down going forward. If it's a very simple, minor change that isn't very consequential, then maybe it's all right to have a higher threshold or to ship under more kind of lax considerations. But again, it's about this choice of how strict should this threshold be. But this threshold, or how much risk you're willing to take on when shipping experiments, only can be controlled with something like alpha if you're not making the kinds of mistakes that Ronnie's talking about, and if you're not, and if you're avoiding these following issues. So when is that significance threshold actually reliable? When can you say, yeah, I'm pretty confident this is a real result? If you catch yourself saying things like, let's just run it longer to see if it becomes statistically significant, which is something I hear all the time, or The goal metric is flat, but these leading indicators are positive. So let's just ship it anyways. What you're doing is you're undermining that contract you've made with yourself about this is kind of the amount of uncertainty I'm willing to tolerate. So one of these issues that's actually already been called out in the chat with respect to SRM, so I see y'all are already on it, is a problem with peaking. So if you don't stick to that planned experiment sample size that you come up with in your power calculation, or you increase the runtime, there's a really good chance you're inflating your false positive rates. So there's two forms. One is a pretty common one called stopping early, right? You look at results early and you stop as soon as you see some stat sig results. But there's another kind that's a little bit um, can be less damaging, but it's also a problem, which is just saying, hey, I'm going to run it longer. So you hit the planned runtime, and then you just decide to run it longer. So I'm going to focus on that latter case because I think it's a little bit more interesting and it seems a little bit more harmless, and ask how big of a problem is that? So let's imagine you run an experiment with no impact, so that it's an experiment where the null hypothesis is true, there's no effect, and you do it for your planned duration. But then you say, let's monitor this to see if it becomes stat sig. And then you kind of check every day after that, or every time some new data comes in, you kind of check to see if it's reached significance yet. In this table, you can see I have this type 1 error rate, which is what you're controlling with that alpha value. Like if you just run it for your planned duration with an alpha of 0.05, you get the expected 5% type 1 error rate. But let's say you run it for 2 weeks and then you run it for another 2 weeks, checking regularly after that 2 weeks has passed to wait for it to reach stat sig. In that instance, your type 1 error rate has ballooned up to 17%. And the longer and longer you run it, the higher this type 1 error rate is. There's other conditions where you can show, like Netflix did in this simulation I linked down here, where you get these huge erroneous early stopping numbers. It all depends a little bit on your data setup. But it also, like Ronnie was talking earlier as well about underpowered tests, peaking can also inflate your estimated effect sizes. So because you stop early when something is positive in stat sig, what that means is it's actually normally overestimating your effect. And so you don't actually know kind of how big of an effect your experiments are, your features are having. A second common problem is one of multiple comparisons, where if you test enough metrics, one will eventually look significant by pure chance. So this is a very kind of well-known, I think, in the when you like start to learn about causal inference or experimentation, XKCD comic, where this person is saying, hey, jelly beans cause acne. So somebody's like, okay, let's verify this. Let's run an experiment. Let's do some investigations. The scientists come back with their beakers full of jelly beans or whatever, and they say that there's no relationship between jelly beans and acne. But then somebody has a hypothesis that, actually, it's certain colors that cause it. And so then they run 20 different experiments where they're checking different color jelly beans to see if they have a relationship with acne. And you can see up here in the top right, they found a link between green jelly beans and acne. That's the headline that gets published. All of these tests were run with that 0.05 threshold. And so you publish with these, big numbers saying we're pretty confident everything is looking good. But then, of course, this is just an artifact of the number of tests that you're running. So if you end an experiment, if any metric is stat sig, but actually in this experiment there's no impact, how often did you make that wrong call? So again, how does the number of decision metrics in this instance inflate that type 1 error rate? If you just have that one decision metric and you do everything correctly, again, you're at that 5% that you expected and that you said, this is what I expect from my type 1 error rate. If you have two, that goes up to 10%. If you have three metrics that you're relying on to see if any are stat sig, then that jumps up to 14% and so on and so forth. These issues also compound with one another. So if you actually look at the combination of having a large number of increased number of comparisons, as well as an increased duration runtime, you can see, for example, that let's say you have two key metrics and you want to run it another 2 weeks just to see if it reaches stat sig. You're in this center circle, the center of this table here. You're at this 30% number. So now when you've set this threshold of 0.05, but in reality, 30% of the time that you're shipping this experiment, if there was no effect, you're saying that there is an effect. So this is going to be really misleading. And if we tie it back to the concept Ronny introduced earlier of false positive risk, where you have maybe a 15% win rate in the background, you end up with the share of your wins being comprised of even more actual false positives. So in that same sale, you get up to a 47% false positive risk, and this is only considering the winners, the half of the tests that you're shipping if they're positive. So that's a half of the things that you shipped actually had no impact in that scenario. So both, it's important to say when I set my threshold to be honest with yourself and say, okay, is 0.05 the number I want? If it is the number I want, am I doing these things that are undermining that trust? Am I just running it longer to see if it becomes significant? Am I just checking to see if there's any reason to ship within the results? So what are the solutions? Well, do a power analysis and stick to the plan, right? Have this outlined up front. Say, here's what we plan on doing, and make sure that you're honest with yourself about the time that you're going to need to run this experiment to get results that are actionable for you. Also, strive for that single goal metric and design power for that goal metric. If some reason these aren't possible or there are trade-offs that you can't do to have only a single goal metric, then you can consider some like multiple comparisons corrections, which will hurt your power in the sense that require because you're checking across multiple results, but it does allow you to have those multiple decision criteria. If you want to peak and stop early, then you can use something like a alpha spending approach where you're only looking at certain intervals, or sequential testing if you have a really robust data infrastructure where you can check kind of after every unit comes in. So that depends a little bit on the use case that is for you. But at the end of the day, what I want to highlight is that you should be honest with yourself, and this goes to some of the questions that are in the Q&A, which I'm excited to get to. It's like, what are the costs of my experiment, and what is the amount of evidence I can get out of it? So be honest about what you're trying to get out of your experimentation program, and figure out whether those costs and trade-offs imply a stricter, like a 0.01 or 0.001 threshold, or more relaxed threshold. But then once you pick that number, you want to make sure that all of the checks that Ronny called out are being followed. The two issues I'm talking about aren't undermining these thresholds you've picked. You want your experimentation process to honor those significance thresholds. The goal isn't to make experimentation impossible. It's to be honest about what the analysis you're doing is, so that as a decision maker, you know what are the trade-offs I'm making when I'm shipping experiments. Great, so that's all I've got for that. We're going to pivot over to the Q&A, but before we do that, we're going to do a raffle. So I've got the names here. Give me 1 second. One second, everybody. Just seeing if I can copy and paste. Let me move this here. All right, I think I've got all the names in here, and we're going to draw 3 winners. So Maya, 1, Jabir, and Ryan. So Samaya, Jabir, and Ryan, thanks for sticking around. Our team will be reaching out with contacting you via the email you signed up for entries into Ronnie's classes. Great. Well, with that, let's switch it over to the Q&A. And I think there's some great questions here. I think the main one that I'm sympathetic to as somebody who works at an experimentation platform that is B2B, is this first one from Holly in the Q&A, which is they had a question about power. So for products with lower user counts, like a B2B product, what's the realistic recommendations for teams? Should we just not do A/B test, or should we ship slower and wait for power? I have my thoughts, but I want to hear what Ronnie has to say about this.
Okay, well, I was hoping to hear your thoughts first, but I'll go first since you're asking. So first of all, I will admit that B2B is much harder to run for A/B tests. We, even at Microsoft, on large products like Office, we had problem getting significant power if we were trying to do the B2B versions and randomizing by the companies that are buyers of the product. At Airbnb, we did a couple of things that I think are useful for you to know if you're in a B2B setting. One is use Cupid, right? Cupid is a variance reduction technique that allows you to get more power by looking at historical data. And because in a B2B setting, the customers are repeat customers, you get a huge boost to uh, to your power. And just to tell you, in a B2C setting, when we wrote the first Cupid article, we said at Bing it was about 50% reduction in the sample size needed. At Airbnb, it was like a factor of 5 to 10 reduction in the sample size that's needed. So that's, a free, sort of a free lunch that you get. Apply Cupid. The other thing is, in a B2B setting, you may need to go for larger MDEs. My sort of guidance of, all the results are small, you get 1%, 2%. That's usually in a B2C setting. If you're in a B2B, you may need to say, we're going to make changes and our customers visit us a lot. And therefore, we are going to go for a higher MDE. And then the last thing is, as you said, you may have to run the experiment longer or, ship slower because it is in a B2B setting. So these are sort of my three top of mind thoughts. I'll let Luke add
Sure.
his own version.
Yeah, I definitely think, yeah, in any low powered setting, but it's important to look out for, opportunities like variance reduction techniques. I think Ronnie is right. Um, you will often have, our GrowthBooks users who run experiments, they log in every week and they're running experiments. And so we actually do have quite a bit of pre-experiment data that can be used in a tool like Cupid. So we have very sticky, dedicated users. And so because of that, those techniques can be pretty powerful. But my answer is kind of at a higher level, I would say, and it's a question of how experimentation fits into your overall information ecosystem. Because we have power users, we get a lot of feedback one-on-one. And so then the question is, how can experiments, when I'm not going to have the power to get super precise results, how can experiments fit into that overall information ecosystem, right? So for us, certain flows, it's just really important for us to test that we're making sure that we're not cratering things or we're causing, one problem to sneak through at a very large rate. But we're honest about saying the best we can do with this is rule out these negative outcomes. So you could do something like a one-tailed test that actually is like a non-inferiority test. So these are all different ways to kind of relax how strict your experimentation program needs to be. But the goal is to be honest instead of just saying, okay, we're just going to have like an alpha of zero point 0.4 and it's stat sig or something like that, right? Be more honest about what you're actually able to get out of your experiments. That's kind of the higher level take I have. That said, like, I think if you kind of reframe the problem of saying, let's at least make sure we're not shipping like duds with data and make sure we have other data streams that are helping guide our direction, then it can kind of tell a comprehensive story about what's happening. But that's just the reality of being in a kind of underpowered setting. I don't think the solution is not to run A/B tests because at the very least you'll get to see like metric levels, but it's about being honest, right, with yourself about how much you can actually learn from those tests. Um, thanks for that. There was a related question actually about from Upendra. Um, and it's very similar. Trigger traffic is small and we're always underpowered. So I think we can kind of skip going into depth here. But one of the interesting questions is like, how do we avoid like the winner's curse burning us? I just wanted to say that one of the interesting things here, and this does require a bit more sophistication, maybe more data, is that all of these issues about shipping false positives and having a bunch of stuff that is kind of misleading you, um, a very powerful tool is to retest or use something like a holdout to combine a bunch of tests and look backwards, and it'll help you understand, okay, if I just summed up these effects and they showed I had, an increase of conversion rate of 10% over the quarter, but actually when I do this holdout, it's only 5%. That difference can help you understand like how much you're misleading yourself. So doing holdouts is a really powerful way to kind of get at how big the winner's curse is kind of hurting you. All right, let's see what else we've got here. few more questions. Let's see if there's anything we should answer
Well,
live.
you should sort by upvotes, and I think we should take the
Yeah, I got you.
logistics
I'm
question.
sorting. The next one here is how to properly use metrics like number of views per number of ads when randomization is at the user level. So it sounds like something like a ratio metric where your denominator is not the same unit as the unit of randomization. Tools like GrowthBook will properly account for this in the uncertainty estimate in the final experiment analysis. And so in the case of power calculations, you just need to make sure that you're using that same kind of uncertainty when running those power calculations. So like our in-app tool, when you pick one of your ratio metrics to do a power analysis, it'll automatically account for this fact. And it'll look at your historical data to make sure that it's doing the right calculations to predict what your power would be for these kinds of ratio metrics. They
Yeah,
tend to
I'll
be
just add that the the keyword here is the delta method. So there is something called the delta method that allows you to correct your variance for metrics that do not have the standard variation like ratio metrics, and you can certainly use those here.
Yeah, for sure. Um, and that,
By
yeah,
the
that
way, Luke, just to highlight, I hit answered live on the first question, so the highest voted question was actually skipped by you, but we can
which
go
one
on.
was it? The Holly one? No, we answered that one from Holly. That was
No,
about
it
the
was,
B2B.
well, I don't know. Somebody clicked on Upendra's question, which is now under the answered.
I see. Sorry. Yeah, I was moving that one through because it was a very similar question
Okay,
about low powered settings.
got it.
Yeah, great. So next one here from David. Is Bayesian A/B testing affected by low power, low sample size? Would a Bayesian A/B test on 300 users in the example presented also have the same conclusions? I'll just jump in and say one thing, the only difference, let's say it this way, you still only have 300 users and the evidence that was presented to them. What you can do in a Bayesian test is bring in prior information that can help you kind of have that free power from some previous evidence you have. However, I would say that being totally right and kind of solving this problem is misguided. At the end of the day, you still only have those 300 users to update those priors. So what you're doing is essentially relying more and more on your priors being right when you have those low sample sizes. And that can be a risky proposition. But yeah, Ronnie, I don't know if you wanted to add anything to that question from
I
David.
mean, our I'll answer it this way. If you know a lot about the problem so that you have informative priors, then Bayesian can help you. If you're using what is typically done, which is to use uninformative priors, the alignment between the Bayesian approaches and the frequentist approaches is very high. And there's some references and posts out there. Some companies have implemented both, and they've continually show that you get very similar answers under non-informative priors. Now, again, if you have some domain where you have very good understanding, in manufacturing, then you may have better priors that can lower the sample size that you need. But I think in our world of online, we get so many results wrong. Thinking that you are going with informative priors that have, strong peaks is misleading.
Yeah. To be honest, actually, for our own experimentation practice, what we have are weak informative priors over the lift, based on the history of just what is a normal range of results. And what this does is it actually makes it harder to make conclusions with only 300 users. It actually widens our uncertainty bounds. And that's because we are trying to be aware of the kinds of Twyman's law type concerns of making a 44% lift on 300 users harder for our own teams to make, right? So actually, Bayesian A/B, we use this prior in our own testing, but the goal is actually to make it not to like get false certainty, but to actually more accurately capture how unlikely a large result would be with after only 300 users. Great. Let me sort by most upvotes. Ryan asks if, oh, this is a good question. If over a week, every day on a 50-50 A/B test, we see a better conversion rate on one arm of the experiment, is this something we can take as a positive sign that it is? So essentially asking if on Monday, Tuesday, Wednesday, if each individual day shows a positive lift, is this evidence that the overall experiment is showing an accurate positive sign? Uh, do you want to start, Ronnie? I need a minute to gather my thoughts, but I'm happy to jump in if you don't have
I
that
think
answer.
it's evidence. I think you will see. I would rather just look at the aggregate, and if every day it was better, then yeah, it's very likely that the aggregate is going to be better, and therefore it will reflect in the p-value. I wouldn't try to come up with additional rules. I've seen some companies
Yeah.
do that. They'd say, "Oh, if you've got 3 winning days, then you can call it stat sig." I don't think
Hmm.
those rules have been sort of tested with the proper statistics. So I think you're right that that is good evidence, but this is what the p-value needs to show you.
Yeah. I would say, when does this matter? If the experiment itself is positive and looks positive, then most of the time people aren't digging into like every day. And on average, most days in that experiment are going to look positive. If it's a case where the overall is so-so and you dig in and it's like, oh, a bunch of days it's positive, then you're suffering from that same kind of multiple comparisons, p-hacking, and looking for positive evidence issues. So I just don't think it adds a lot of information over the overall effect. One
I
other,
would say, by the way, something else, which is if I see an experiment that is positive every day and then one day is very negative,
mm,
I'm going to look for whether there was a problem that day. We've had cases where, okay, there was an outage or, something like that happened, but that's a way to, again, check the trust of your experiment. If there is a very big deviation from the average treatment effect on a given day, then I will investigate if there's some reason for that. And again, you got to be careful. It's got to be a real reason. You can't just say, "Oh, I think this day's bad. I'll filter it out." You got to find the reason.
yeah. I will say one other thing is, it's nice to like the time dynamics are also important when it comes to like primacy and novelty effects, but because you're looking at even more results, it is important to be wary of, again, false positives in that and not over interpreting that information, but it can be useful for that. All right. We only have time, unfortunately, for one more. There's a bunch of these that have one kind of up up vote. And I think one thing I'd like to chat about from these that is I think David's question here about in very low powered settings, could we also look into proxy metrics which are more sensitive, such as add to cart instead of revenue per user? Um, yeah, so one of the things to call out, this is a good question for all of those of you that are asking about underpowered tests or whatnot. Even if you have an eventual business goal that is a little bit more downstream, if you have a reasonable mental model about how those more kind of upstream, more sensitive metrics correlate with those, then I think it is definitely a valid approach to use those more sensitive metrics. It is important to make sure you're not just like getting people to add to cart and then they're all falling off. So again, that eventual goal metric that's downstream, it could be super important to, again, be honest. Let's make sure we can design a test that can rule out a bunch of like really bad outcomes on revenue, but while we're still shipping on this more sensitive proxy metric. But yeah, Ronnie, I don't know if you wanted to add anything to that.
Yeah, no, I'm a big fan of using surrogate metrics. And I think in many situations, that metric that you really want is just something that you can't compute. It's too high variance, it takes too longer, and then you run some experiments to prove to yourselves that these surrogates are going to be good. So we have done those tests where we said, okay, here's a surrogate metrics, or here are candidates. We evaluated them and then decided that yes, some of them are good. We trust them. We believe there's a causal effect, and therefore we are going to use this in our experiments. So absolutely yes. And I talk a lot that in my book on the OEC chapter and in my class, and give examples of surrogates that have been used.
Great. Yeah. Well, we're at time. There's still great questions in the chat, but we're at time. Thank you all so much for joining. The recording is going to be emailed to you all the next few days. You can stay connected with the GrowthBook community on our LinkedIn. We have a community Slack as well. And of course, you can kind of sign up to start experimenting in GrowthBook right away. Thank you all for joining. We'll be reaching out to those of you that won that raffle and hope to see you all in the next one. And thanks so much to Ronnie for joining. Thanks, everybody.